Event-driven architectures are great, but they do come with some tricky parts that we as developers need to take into account, especially when it comes to race conditions. There are three major types of race conditions that usually happen within those systems: out-of-order events, distributed conflicts, and phantom failures. And in this video, we're going to try to understand what they are, and you're going to learn how to fix those. By the way, this video is sponsored by Coder, but I'm going to talk about it in a couple of minutes. Now, let's try to visualize these type of race conditions and understand how they might look within an event-driven architecture. So let's say we have a publisher, we have two consumers. As you can see, they're separate services. We have a RabbitMQ message queue. And finally, we have a database where these messages are going to be stored as transactions. Now the publisher sends message 1, it goes through a message queue, and in a round robin fashion, one of the consumers receives this message, and the second message also goes right away, and the second one ends up in consumer 2. But since one of the consumers is slow, as you can see, message 2 is being saved in the database first, and then message 1 comes later. Now, this is a race condition because the events were sent in a different order and they were saved within a database in a different order. Now, it doesn't mean that it's always an issue, but there are systems where you need to make sure that the order is preserved. For example, payments. You cannot overwrite the balance by an older entry. One of the methods to eliminate such a case is called out-of-order events, or actually, this is one of the problems called out-of-order events, and this graph is how you eliminate that. So let's say we have the same publisher, pretty much the same graph. The only difference here is that we're using this technique called last process tracking. And how do you do that? Whenever one of the consumers receives the message, let's say this consumer received 3 and 5, and this one received 1, 2, and 4. Obviously, 3 should come after 2. Now, last process tracking, it somehow reminds us of linked list, right? But it's somewhat similar. It's not really a linked list. We're going to have two different arrays. Last processed one, and this is where messages are eventually ending up, and this is what is being saved into the database. Now, last processed one is going to be keeping track of the last processed message sequence. The sequence is, in this case, is 2. And we know that if the last one was 2, the next one is expected to be 3, as you can see here. But in this case, what we receive instead is 4. Now, 4 is not 3, meaning we're a bit ahead and we are missing one message in between. So we're going to put 4 into a buffer, right? We're going to put it here to be able to work with it later. Now, the next message that arrives is actually 3, so which is good. And we're putting it into less processed. And now we are taking a look into the buffer. Does the buffer contain the message that we're expecting next? Because the next one expected after 3 is obviously 4, and then we take it from the buffer and put it into the last process, meaning we're simply saving it to the database. Now, how is it gonna look in terms of the workflow? Let's say we receive a message and both consumers need to keep track of what has been processed as the last entry. So we're going to take a look at the database. Let me make this red. And the database says we have message 2, and we compare it to what kind of messages we have. And in case if we need to use the buffer, as we did with message 4, then we're simply going to store it in some kind of a database. It can be a Redis database in this case. I think it's the key value pair, so it's pretty handy. And as soon as our buffer is full, we know that when the next message arrives, then we can check how our database looks like. And if it expects something that we already have in the buffer, then we take it from the buffer and save it into the database. All right. So in the code, it would look something like this. We have a producer and we have consumer. And here I have the third file, which is actually the fix. So let's start the producer, or rather the consumer, and see how this is gonna look like. I'm gonna say node consumer.js, and it started, and I'm going to start the producer as well, node producer, and the producer is simply going to do the following. We're going to shoot 15 messages to aggregate that we have order ID, and we're going to be sending a message that contains an aggregate ID so that we know how to buffer them properly or group them, a sequence ID, and a timestamp. All right. Now let's send this. The messages are sent, and as we can see, the messages arrived in a completely different order. Now, of course, we're doing cheating here because we're introducing a manual delay to kind of show that services might work in different tacts and some of them might be slower, but this is probably what you're going to end up with if you work in such an environment where one of the services is probably slower. How do you eliminate that? As we already learned, we have pointers, which is the last processed one, and we have buffer, and we're simply having a while loop where we check which item has been expected the next, and if it is expected, we somehow delete it from the buffer. In this case, the buffer is simply an array or an object, and it's not a Redis cache, but you would usually want to store it in a separate database, because if this service goes down, then you have your sequences and your buffer saved somewhere. And at the end, we're simply going to increment the number of the expected. And the rest is pretty much the same. We're simply going to consume the messages and send an acknowledgement. Okay, so then let me tell you about Coder a bit, because you're probably seeing the name here and you're wondering what it means, because I also mentioned in the beginning. Well, Coder is an AI development infrastructure where you, developers, your teammates, and AI agents can collaborate on a specific project. What do I mean by that? You probably saw all of that infrastructure with different databases, Redis, Postgres, RabbitMQ, different types of consumers. If you run all of that on your local machine and your CPU with a RAM is probably going to suffer at some point, especially if you do some AI development and run some AI agents locally, your computer is going to get slow. Instead, what you can do is use Coder, and you can create a workspace. Well, in this case, my workspace is defined here, and I'm using it for my demo, but I also have an AWS workspace. And workspaces are based on templates. And cool thing is you can create different types of templates based on AWS, Azure, DigitalOcean, Google Cloud. You basically have a lot of flexibility. And whenever you create a workspace like this one, you and other developers can actually be onboarded to this workspace. And based on what you defined in your template, and the templates are Terraform-based templates, so you can define all of the infrastructure that you saw on my graph and then make a workspace out of it. As soon as you have a workspace and your workspace is on and running, you can collaborate here. The cool thing here is that, as I mentioned, you also have some AI agents working next to you developers, meaning you can have some tasks here. For example, you can say, check the PRs in the background and tell me what you think about these PRs. Now, how cool is that? This is not only it. As I also said, Coder is very flexible to use and it's completely free. So definitely go check it out. And the thing that I like the most about it is how versatile it is when it comes to different operating systems. You can basically create any operating system that your workspace is running on. You can use different types of tools like Jupyter, VS Code, pretty much connects to any IDE that you have locally. You can use any AI agents or coding agents that you want. Claude is probably the most popular now, and these AI agents are based on it. You can make them based on it. And of course, anything else that you have within your infrastructure is available at Coder. So go check it out. The cool thing is also that it's trusted by Fortune 500 companies such as Palantir and Dropbox. So it's a really cool product that people trust and organizations trust. So go check it out. And with that said, we're actually going to go back to the code. And we're going to talk about the second point, which is called distributed conflicts. Now, what are distributed conflicts? Let's go to the Blackboard and discover that. Distributed conflicts are happening in the following case. Let's say we are a banking app and message 1 is giving us $90. So someone transferred us $90, or our balance is 90. And message 2 tells us that our balance is 100. So when these messages go through the message queue might be slow, all right? It might be down. And then the publisher has to resend. So there are many cases where the order might be messed up within a message queue. And then when an order is being messed up and the messages are coming in the wrong order, then all of that is saved in the database in a completely wrong order. So first our balance is going to be 100 and then our balance is going to be 90. So we literally lost $10, as I said before. This is very critical. When it's about money, we need to preserve the order here. Now, what can we do? Well, we can introduce something called versioning. All right. If we do versioning, we know that the message that came first is version 0. The next one is going to be version 1, and the one after is version 2. And if our next message is saying version 2, meaning we skipped one of the entries, so we need to do something. And things that you can do is probably reject and discard, because if you receive the version 2 and you know that there's no version 1 in your database saved yet, can you override it? Because in this case, we can actually take version 2 and completely forget about version 1 not arriving, because 100 is more than 90, and it's probably okay to have a higher balance. Or you can compensate it, meaning you can calculate the difference between 9 and 10. And if you think that this difference is reasonable, or this delta is reasonable, then you can calculate it on the fly as soon as the version 1, the old message arrives. Or you simply can requeue this, meaning you take this message 1 that arrived later, you send it back to the publisher or to the message queue at the end, and at some point it comes to the front again and being sent to the customer again, and then the customer can process it. Now let's take a look at the code to how all of that would look like. Now the producer would simply shoot 2 events, as you can see, delta 100 and delta minus 30. So we're adding $100 to our account and we're removing $30 from it. Now the bad consumer would simply not care about the order, and it would just read the balance as it is. So let's try to run it and see what it's doing. I'm going to start the consumer. So node consumer bad, and the consumer has started with a balance of 1,000. And we're also going to start our publisher. So node producer, and we publish 2 events. So what do we see here? Balance is 1,000, balance is 1,000 when both events arrive. And then the event 2 is being written first, meaning delta minus 30 and then delta 100. But at the end, we still do end up with the right balance. Why? Because we used the following technique. We actually compensated. So it's not such a bad example, but if you don't do any of these, you're probably going to end up in a bad situation. Now let's take a look at the good example. This one is optimistic. So optimistic meaning we are checking the state in advance. So the only difference here is going to be the fact that we're going to have this method called persistence compare and swap. And if we go inside it, we're going to check that whether the current version that the database expects is the one or is the version that we are also giving it. If not, then we'll indicate a conflict and simply requeue it. If so, then we simply create a new state and increment the version. So as I said, you have different ways of dealing with that. Now let's go to our last example called phantom failures. And phantom failures are all about idempotency. Now let's say our message 1 is being sent to the consumer, and the consumer is then saving this message in the database. And in this case, we're sending an ACK, which is an acknowledgement to the RabbitMQ that, hey, we actually did receive the message. All right. So what happened here? We did save it to the database, but right before sending an acknowledgement to RabbitMQ, as you can see, our acknowledgement failed because our consumer, for one or other reason, went down. All right. Now we have an inconsistency. Our publisher did not get an acknowledgement from the RabbitMQ. It doesn't know that the message has been processed, but the message has been processed. It's already in the database. So how do you deal with that? Well, there's a thing called idempotency key. And why is it important? Well, it's important because if the publisher now doesn't know that the message has been processed and it tries to send the message 1 again and requeue it, RabbitMQ doesn't do anything and the consumer receives it again. But if it doesn't check whether this entry has already been saved in the database, then we're going to have a double entry. Now, how do we eliminate that? We actually introduce an idempotency key that we also save in the database. And you can make the idempotency key be based on, for example, a user ID and the timestamp when this order has been happened or when this message arrived. And every time when you receive a message like this one, what you're going to do is you're going to create a hash or idempotency key based on its user ID and the timestamp you're going to check the database for this idempotency key. If it doesn't exist there, then meaning this message has never been saved to the database, and you're free to proceed and save it to the database. And finally, send an acknowledgement. If the idempotency key already existing in the database, it means that the message is a duplicate, and so you simply need to reject it or get rid of it. All right, now let's take a quick look at the code to understand how this might look like. And in this case, it's actually rather easy. And the reason it's called phantom failures is that it's an event that's a phantom. It somehow happened, but at the same time, it didn't happen. So the producer is simply going to send one single message, and the bad consumer is doing nothing. It's actually removing the balance, so from the database or saving something in the database, and we're simulating a crash. So we couldn't send an acknowledgement, as you can see here, channel.acknowledgement. We couldn't acknowledge this message, and the producer thinks that, okay, it wasn't acknowledged, so maybe I wait a bit and retry. But the good consumer would do the following. We would create a message ID from this, which is an idempotency key based on the user ID, and let's say an amount. You can also make it a timestamp, and we check the database in advance. If the message ID or the idempotency key is already in the database, and we say a duplicate detected, we're going to skip it. If not, then we make the payment proceed. All right, guys, I hope you learned something new. If it was interesting, let me know down in the comments. And as always, subscribe. It really helps my channel. I'm going to see you guys in the next one. Goodbye.